So hello everyone, thanks for coming and joining the webinar. Now you've heard a lot about the UltraHD model and about observational data from Miriam, and now we move to Earth observation. I want to show you an Earth observation data-based service for the mitigation of heat in cities. So first of all, why do we do Earth observation for that purpose? And I guess some of you may be working with that. Of course, the big advantage is that we have spatially continuous data. So we see it over wide areas and we have repeated surveys, always the same type of data and for wide areas. And in the Earth observation domain, a lot is happening. So we have quite many services and sensors coming up. So for example, we have not only pictures, let's say, meaning optical data of the surface, but we also have further data that are rather analyzing the surface. So we have, for example, temperature measurements from satellites at the moment only at 100-meter resolution, but there are some sensors and missions coming up so that we will have quite far better resolution of something like 30, 50, 75 meters in the next couple of years. So the field is growing, the interest is quite big in these, and it can make quite a difference. So one indicator for urban heat distribution, Miriam and Stefan especially has talked about the 2-meter temperature, so that's the air temperature. But of course, we don't really see the air temperature from space, but what we can measure is the land surface temperature. So the temperature on the ground, which is rather extremer in comparison to the air temperature. So on the lower left, you see a 10-meter satellite image. That's a very common sensor, the European Sentinel-2, 10-meter resolution from our pilot Karlsruhe. And on the right side, you see the same domain in a thermal image. So that's the land surface temperature. The product from the Landsat 9 satellite, similar to the Landsat 8 satellite. They acquire the land surface temperature on 100-meter, but in the end, the product is delivered on 30-meter resolution. So it is not really recorded on 30-meter resolution. But you see here already that park, that's the Stadtpark in Karlsruhe. There's actually a zoo in it that has a quite lower temperature in comparison to the surrounding city. So this is the data that we work with. On the one hand, these optical data on the left side. On the other hand, these data that are derived from thermal bands in the mid-infrared region, the land surface temperature. And what we want to do with our Earth observation data is help this city planner, which might ask, how does the urban temperature change when I do a special construction project? So you've heard from Stefan Horn about the UltraHD, and actually this service for supporting the heat mitigation in cities, this called simulation service, where you can run scenarios. Stefan has shown it a bit. And in our CityClim project, we have two versions of it. The one is based on the UltraHD model that Stefan has presented. And now what I will present you is an Earth observation data-based one. And so not to confuse you, but to be clear that they are not making each other obsolete, but they are kind of working together. I noted down what are the differences in between these two. So you remember from Stefan's presentation that the UltraHD is a 100-meter resolution, very well resolved weather model, a process-based weather model with a very fine resolution of processes that are relevant. And therefore it can derive or simulate a quite high number of parameters, being it temperature or winds or pollutants and things like that. Of course, that comes on computational expense. Stefan said it's taking around about a day, the simulation of 3 days, and it needs an initialization of a new nest. So it's not so simple to set up. However, it's very accurate because it's process-based. And you saw in this very long list of Stefan that it ran every 6 hours, so there are quite many weather data already available. And in comparison, an Earth observation data-based engine, we don't have a real process representation if we want to derive information on heat from Earth observation data. but we are working rather with direct or indirect relationships of, for example, vegetation that we can detect from a satellite to heat. This is, in comparison to this process-based model, this is rather a low computational effort. And so the engine that we produced works rather in seconds and not taking a day. It is easy to set up for a new city because you basically just have to give the new bounding box of the city. But you can, of course, only do it when you have data. So when there are clouds or if the satellite is not there, you don't have data. So you can't do it for every day in comparison to the process-based model. So I said they are working together, and for us it was a good thing that we could have two of these simulation services in our project. So our understanding is that we use the EO-based engine to help our city planner for a quick testing of any number of scenarios. So when he wants to screen all the options, but then if he takes it down to a smaller number of scenarios and wants to have a really detailed view on how the processes are, how many parameters change, then you go to the process-based engine and use the UltraHD model. So these two services are complementary to each other. So going a bit into the methodology, what are we doing and how does it work? This is the very logical chain. So we have our city planner on the one side. He goes to an online tool that Stefan already showed a bit, this scenario tool where he can modify the urban configuration. Then something happens, and in the end, the user gets an answer on how much the city climate will change due to the identified modification. And then he can think, do I like it, do I not like it, and apply iterations of options. So this is what the user sees. But now to tell you how it really works and what is here in behind these wheels. So the database, I already told you, these are multispectral, meaning optical remote sensing data from Sentinel-2, the European satellite system, and the American Landsat 8 and 9 system, and a DEM is the digital elevation model. But in these DEMs, as Mr. Birami already asked, they are normally provided by the cities themselves. But all the others can, the data are coming from the Copernicus network. So what we do is derive some parameters that describe the urban surface. That's on the one side, the imperviousness, that's the degree of sealing of the surface. The NDVI, many of you might know, that's a vegetation index telling you how much vegetation is there, how much green actually is there. And then two metrics that are distance metrics. So for each pixel, we calculate on how far is it away from vegetation or how far is it away to water. Because you might know that water might or has a cooling effect of the surface. And the same with vegetation. The cooling effect of water is higher or more intense and it lasts longer. So with water, it is assumed in scientific studies that this cooling effect reaches to a distance of about something like a kilometer in wide. But of course, it depends on how big the water surface is. And lastly, the 3D urban geometry, that means like building height, the building roof index, how many roofs are within a pixel, the percentage of roofs. And the target variable is the land surface temperature, as I said. So what we do in the end, we calibrate a neural network, making a relationship between these describing layers, describing the urban surface, and this target variable, the land surface temperature. And then in the end, when we have this calibrated network, then the user can modify the urban configuration. This triggers a modification of these layers. And then we can simply calculate the land surface temperature. And this is basically the answer that the user gets. So I hope this is clear. Now let's go to the online prototype. This is already the surface that the online tool that Stefan showed you. And now our engine is located here in the back, and it has 3 steps: information, editor, and result. And we will go one to the next now. So in the info button, you actually can examine the patterns of heat in your city. And what you see here again is Valencia in Spain. That's actually a very green city. It was the green city of 2024. And actually in every square that they have in the city, they have trees, which is not very common for a Southern European city. So Valencia is doing a lot. And what everyone who has been there knows, the River Turia. That's an old riverbed that is not active anymore, but it is actually an urban park. And you see here in this image, I mean, I know that these houses here are a bit distracting. They cover the LST information, but you see clearly that the River Turia is much lower in terms of temperature than the rest of the city. And although it has a lot of green spaces, Valencia is heating up quite a lot in hot days. So they have an intensive problem with heat in the city. And now what I want to show you is an example here on this Jardins des Réals. That's a big urban park. It is partially sealed, but partially quite green. It has trees there. And we will have a closer look at this one. So in the second step, we as a user create our own scenarios. So this is our jardins. And I was quite blunt here. I completely sealed it with houses. Sorry. So you go to this tab and you draw a polygon, no matter if one or more. And then a display is coming up saying to which land use do you want to change it and which height does it get. So if you get, and I put all buildings here, you can also define the height of the buildings and making it really skyscrapers or smaller houses. And then you select your model. That here is the 2D model, so neglecting the 3D geometry information. And later on, you will see why we neglect it here. And then you take a reference. So we have this engine running for average and extreme summer days of the last couple of years. And then you can say request, and that actually brings you to the last tab. That's the result tab. And here you select again your scenario so that it knows which one you created and a timestamp, for example, when you change your scenario. And then on the main window, you have a slider in the middle where you have your before picture here. So the real picture for this extreme summer day in 2023. And on the right side, you have your result. So the modifications that you implemented. And you already see here, it gets worse. So when you seal these, so in this result tab, you're evaluating your scenario. And now in our scenario, you remember we completely sealed it and it was a nice cooling spot, especially the southern part of these jardins, because this upper part is a bit more sealed with this fountain here, for example. And all this is gone afterwards. So actually what we have in the end is over this entire area roundabout, we have a land surface temperature difference of something like 4 degrees. And if you translate that to air temperature, of course, it will not be 4 degrees because surface temperature is always more extreme. And it's not a linear relationship, so I can't tell you how much it is in air temperature, but it might be something like ½ degree to 1 degree to a bit more. So that's how the engine looks at the moment. It's a prototype, it's implemented, it works for 4 pilots of our project, so 4 European cities. A word on the performance of the service. So the land surface prediction model, of course, you can calibrate and validate with the data that you have. And if we do that for multiple cities and multiple points in time, so data sets, then we get R squares. So that's the correlation coefficients of something like 0.68. That is kind of not a perfect model. It's not. But I think for such an application, it's a realistic R square. And the RMSE, so that's the mean error, is ½ a Kelvin. But this is very much okay, because if you consider these land surface temperature data sets, if you derive them from satellites, they have an error of the absolute temperature of something like 1 to 2 Kelvin. So the engine here has, in terms of error, it has quite a good performance. Some general observations that we had from all the data sets that we modeled and all the scenarios that we ran. we do see that the large-scale heat patterns in the cities itself, they are coupled to the distance of water and to urban green, because they have this cooling effect. You see that here, that's Karlsruhe again, that's this urban park that we had earlier. And this is like in Karlsruhe, that's the main pedestrian zone. So that is kind of the hottest. I don't actually know what this, sorry, I know it. It's kind of a conference center or so. So that's a very sealed spot here in the city. So that's, so the degree of sealing, these small scale heat patterns, that's linked to the imperviousness in a city. And we do say actually a little influence of the 3D building geometry. And this is also why I left it out earlier in our trial. It doesn't have a lot of influence, but that might also be an issue. At the moment, these land surface temperature data are acquired on 100-meter and delivered on 30-meter resolution, but that might be too coarse for cities. However, the newer sensors, as I said, they will bring this information. So this engine is also an investigation into the future. So what we do actually wanted to do is a comparison with historical construction examples. So not modeling what changed, but actually seeing what has changed and comparing it to our engine. This was planned and now we couldn't do it because we didn't fit anymore in the project because an intern resigned. We still have it planned. We try to do it because it makes sense. So in summary, I showed you an Earth observation database service, which we can use to see the effects of the city configuration on the urban heat distribution. This is particularly important for climate adaptation and mitigation matrices. And it directly answers the question on what can we do to improve the heat accumulation in the city. It runs and it shows it on 30-meter spatial resolution, but it can be improved when newer sensors come up. We do it for average and for extreme summer days of the last years. And it's a very quick implementation of this tool. So we can run it for new cities. If we have the CityClim services running afterwards, and you directly get an answer to your scenario. So it takes several seconds until you have the answer. The comparison to the UltraHD, for this Earth observation database engine, we just utilize direct or indirect relationships, and we don't resolve the detailed processes that the UltraHD resolves as Stefan has presented it. So when it comes to really detailed observations and assessments, then we should use the UltraHD engine. And for all of these, as you saw on the website, a prototype is existing. So that's already what I wanted to show you on this engine. Thank you very much.
Thank you, Anita. And oh, we already have the first question. This is for Anita and also Marco Spagnoli, who worked on the EO-based service as well, might answer. And the question is, did you compare your land surface temperature predictions with in situ measurements?
So the land surface temperature observations, what the satellites observed, they are kind of calibrated. So they are frequently compared to, so that the product that Landsat is delivering, that this is actually accurate. So this is happening. Our land surface temperature predictions, that is kind of the calibration of the engine. And this we didn't directly compare to measurements because there will necessarily be an offset, but that also depends on how you measure. And yeah, that is always, I mean, what is right or wrong? Also, the measurement on the ground is not correct. But we do compare it in terms of we calculate the deviation and this correlation coefficient. So that is actually telling you on how good this model performs. So not with in situ measurements because there will be an offset, but that comes from the sensor determination, but we calculate on how good our engine is.